Welcome to the part two of coding in assembly. Yesterday we had a really fun session. It was more about computer architecture rather than assembly itself. So hopefully today we'll be learning some of the basics. Yesterday I mentioned a couple of those, but today we're going to go a bit more in depth into those, and we'll be coding into one specific architecture, which is called ARM. So we'll be learning about that one. No worries if you're not understanding exactly what I'm saying. I'm going to go really slowly. And then we are going to do three coding exercises together, um, about simple stuff to do on assembly. And I'm going to share with you a simulator online that I used on my university classes, which is really nice, to be honest. You can see how the registers are being filled and how each instruction is being executed. So hopefully you will find it as interesting as I did back then. But yeah, really excited to see you all here. Don't forget to check in on the link that I sent over on the chat. It is day three of the beginners week, so we still have a couple more days to go. So continue attending to the streams, continue doing the different challenges, and attending sponsor streams as well in order for you to claim your swag for the week. So in my personal opinion, I always like beginners week because you see a lot of diverse hackers. So people that are here, that are new, or people that are just starting to learn about technology, or perhaps we also have experienced hackers. So yesterday at the stream, I realized that there was a huge variety of people that was watching it. So hopefully today my stream can be appealing to all different levels of people that are into tech. So I always like to go into the basics, but I also like to add some complexity in it for people that are already experienced in the topic. Um, and yeah, lastly, before we start, I'm just going to say that I'll be now doing more streams related to robotics and engineering rather than software engineering. So yeah, you'll be seeing much more of my streams that are related towards the robotics side, because with me it's about two sides. So I can either be super into CS or I can be super into robotics. So I think I've done a lot of streams about CS and AI itself, because I that's something that I always like to talk about. But I think now it's time to do some more of the engineering part for all of those careers that are into mechanical engineering, electrical engineering, robotics engineering as well. So we'll be seeing all of that on my upcoming streams as well, hopefully for the next Global Hack Week that will be coming up as well. Awesome. So I'll start by sharing this, and we'll be getting started with the part two. Hi there. And no worries if you were not able to attend part one. As I mentioned on my Discord message, they are not related. So if you were absent for part one, we're not going to do like, this is not part two, as if you are, as part one is dependent of part two. Like, they're completely independent. So no worries if were not able to be there for part one. For part two, we're going to get our hands of some workshops and some exercises that we'll be doing, and we'll be seeing very specific content about this assembly language itself. So just to introduce myself, which I think I didn't do that, my name is Jocelyn. For people that I already know me, I'm a coach here at Major League Hacking. I also like to stream, and I'm also in the fellowship as well. So there's a lot of MLH going on in my life. I like salsa dancing on my free time, and I also collect, well, I have a huge collection of Minecraft bee plushies, or just bee plushies in general. And yeah, I study robotics in college, so that's something fun, and that's why I'm bringing these topics to you all on our Global Hack Weeks. Hope that you're having fun so far on this set of streams, and yeah, let's get started. So for today, we have a very packed agenda. So hopefully, I'm going to try to make this for 2 hours, because we need to finish it in 2 hours. So let's see how much we can advance. First, we're going to learn about different chip architectures so you have more insight on not only assembly in itself and what it is, but also the different types that are out there and how to make a difference between them. Then we're going to see some specific instructions in this language. It's called ARM v7, which is a specific assembly language. You'll understand more of this in a while. And then we're also going to use an online compiler called CPU later, which is the name. It's fun. You have to admit it that it's the name is fun. So we're going to be using that online compiler in order to test our assembly code and see how the registers are moving. If you don't know what a register is, no worries. I will explain it further on. And for the people that were on my previous stream, well, you already know what a register is. And finally, we're going to code 3 different examples with the instructions that we learned. And well, my goal here is that hopefully after this session, you will know how to code in ARM v7, which is an assembly flavor. So it's a different, well, it's not a different, but it's a type of assembly languages, because there are different languages, as we all know, in coding, and assembly has different languages as well. So we'll be using for this stream ARM v7, which was something that hackers were asking me on the past stream, which flavor of assembly we were going to be using. I mentioned that we were going to be using leg v8, but I changed it because I found a really nice simulator online that I would like us all to use, and that simulator supports ARM v7. So we're going to be using that one. All right, so if there's not any more comments or questions, then I'll be getting started with our first topic for the day, which is ARM v7. So I know that I mentioned this a lot, and you might be wondering what are those weird letters, or I don't understand anything at all. So ARM v7 is just one of the many flavors of assembly language that are out there. So you can have different flavors of assembly. It's not only one, as in the same way that you have different programming languages. So you have Python, you have JavaScript, you have Java, C++, and so on. So you have many different programming languages. And in assembly, it works the same. So you have different chip architectures, which means that you will have different flavors of assembly language. You can think it as it's in there. So assembly is related to hardware. So if you have different pieces of hardware, of course, the same assembly language would not work the same for all chip architectures, because the CPUs are just built different. The architecture is completely different. So if you try using one type of assembly in your ARM v7 that's not compatible with ARM v7, then your code will just not work. You can see it as if you were trying to build a Python script in a Java editor. So of course, you're going to get a lot of syntax errors and your code will just not compile, because your compiler will be saying, okay, what is this? Why am I receiving Python when I'm supposed to be reading Java, right? So it's the same with assembly language. Depending on the chip architecture that you have is the dialect that you're going to be using. Simple, right? So just knowing that there's different versions of it. Assembly is not just one thing as a whole, so it's not just one language. So you have different versions of assembly. So now when someone says that they can code in assembly, you can ask them, okay, which architecture of assembly are you using for your code? Because you'll realize that it's different. So the instructions will be different and the syntax will be different. So you might be confused if someone shows you a code in assembly and you'll be like, okay, I went to Jocelyn's stream, but this is not the same. So these instructions are different. And just because they are different flavors of assembly language as well. Missed part 1, really want to know how to get started solid in assembly. No worries. As I mentioned on my Discord announcement, part 1 and part 2 are independent. So right now I'm just mentioning that we're going to be using this flavor of assembly, which is called ARM v7, which corresponds to that chip's architecture. Which, fun fact, this chip was previously part of the Raspberry Pi board. So if you have used one of the old Raspberry Pis, I'm pretty sure they have ARM v7 in there. So if you see the chip, that's like the small black square, which is in here on the middle of the Raspberry Pi, That's most probably be an ARM B7 chip. So in that case, you will be able to code in assembly with that board specifically. And just like that, there's different boards out there that have different architectures, and depending about the architecture that they have is the assembly flavor that they will be having. Okay, and the difference. So key differences on ARM architecture, V7 specifically. So this is a specific CPU architecture, as I already mentioned, and the company's name ARM Holdings. So that's just the company's name, and they decided to call it that way, and that's just V7. It's version 7. You can have different versions as well. We'll be using V7 today, nothing specific. That's just because the simulator that we'll be using supports that one. So nothing in specific about why I chose that one, really. What is different is instruction set. So the different operations that exist in this language, they are named like this. We'll be seeing more about what instructions are in a while. So don't worry if you don't understand this. And then another different thing is the number and names of registers. So for the people that were present on our last stream, you already know what registers are, and it's just large spaces of memory in different cells. Um, so this is named differently depending on the architecture that you are in. If you don't know what a register are, I'm also going to be explaining that more in depth in the upcoming minutes. And finally, another key difference, depending on the chip that you're using, is how numbers are represented and how memory is accessed inside your board or architecture. And as I was mentioning, if you write assembly for ARM v7, it will only run on processors that understand this type of architecture, or this type of machine code. If you try inputting this type of assembly language into another chip architecture like RISC or MISP or any other assembly architecture, it will not work. So it will only work on ARM. I hope this is clear because it's very important for us to know these concepts, right? Because one can know how to code in assembly, but if you don't understand why is it there or the different architectures that are out there, you will just be left with many questions on how it works. Okay, so first topic of today that is very important because we're going to see it on the exercises, and I expect you all to remember. So registers. What are registers? Registers are just spaces in memory. So you have different spaces in every chip architecture. So for the case of ARM v7, they have all the way from R0 up to R15. And you might be wondering what's the R. So R stands for register. So register 0, register 1, register 2, and so on. And each of these registers, they have 32 bits. So R2 is 32 bits, R1 is 32 bits, and so on. And as we might know, or as we are just learning, one byte is equal to 8 bits. So that's the basic unit of computers, bits, right? So if you want to group them, instead of just saying 32 bits wide, you can say 4 bytes wide. So each register in here can store 32 bits. And what can they hold? So what am I going to store on those registers? Why are they relevant? So in there, I'm going to hold all of my information. So you can hold signed or unsigned integers. You can hold memory addresses, or even bit patterns like flags or masks. So right now you might be saying, okay, I know what an integer is. I might know what a memory address is, but what is a flag and what is a mask? So flags and masks are specific types of bit patterns. We'll be learning more of how to identify those, but just keep in mind that registers can store these 3 different types of data. So signed or unsigned integer. Your regulars, 1 minus 1, 10, 450, any integer that you can think of that's less than 32 bits. Because if you do a large integer that's more than 32 bits, then your register will overflow and your program will just crash. And memory addresses. So memory addresses is an hexadecimal address. So if you're familiar with hexadecimal numbers, so basically the ones that start with 0x and then the combination of letters up to A to F, and then 0 to, I don't remember, 0, I think I go to 0 to 7. But yeah, basically hexadecimal addresses is just an address. If if you can see it that way, and the bit patterns, which are just combinations of zeros and ones that represent specific flags and masks. In here, on this stack of registers, you are seeing special registers. So we have the general purpose registers that go all the way from R0 to R11, no, R12, right? And then in here on the left, we are seeing R13, R14, R15. And then you're seeing R13 is used for stack pointer, R14 is used for linked register, and R15 is a program counter. So these are specific types of registers. If you're familiar with computer architecture, you might know what a PC or program counter is because it's on the main diagram, on the von Neumann diagram for computer architecture. And that one is just basically to store the next address. We'll be seeing more of that in the upcoming slides. But just keep in mind that there's some special registers that work for specific things. So if you use them, it means that you want to use that specific feature that that register has. And then we also have this separate register over here that's called current program status register. This program in here, well, this register in here is the one that's related to flags inside our program. So flags, if you are familiar with programming languages, we sometimes set flags in Python or whatever language in order to know if something is true or something is false, right? So this is the same. Assembly also has different flags, and we can identify them using this specific register over here. And then the all other ones that we have, they're just used for general purpose things. So let's say I want to store the sum of two numbers, or I want to store an arithmetic operation in the result of R5, whatever. So all of the results of my operations or whatever thing that I want to do with my numbers and my registers, they will be stored in this stack over here. There's a question over here. Is it possible to get the slides? Yes, I mentioned that I was going to share it yesterday, but I prefer to share it with you today because now it has the whole set of slides that I prepared. So the ones from part 1 and the ones for part 2 as well. Great. So for now, you should understand that registers are spaces in memory to store either integers, memory addresses, or flags. And in ARM v7, the size of each register is of 32 bits. This is important because we can't store very large numbers or very large values because then we will have an overflow in our data. Okay, and as I was mentioning there's some special registers on every architecture. So not only on ARM v7, there's special registers on pretty much any architecture that you can think of. Some of those, we'll be seeing 4 of those special registers. The first one is called PC or program counter. So this is specific register. It holds the address of the current instruction being executed. So if I'm executing an instruction that's adding 2 numbers, then the PC will have that address for that instruction. And what do I mean by address? Address, again, is just an hexadecimal number. So it can be 0x0, 0x01, 0x02, and so on. So the program counter will hold the current instruction that's being executed. And once the user wants to read your program counter, you will get the instruction address, so the current instruction that you're executing, plus 8 bits, because it will be the next one. So you're jumping up on the next one. So PC will always hold the instruction that's being executed. We will actually be seeing PC a bit more once we get to the examples. So I would say this one is one of the most important ones. Then we also have the stack pointer, or SP, and this one points to the top of the stack in memory. So if I have my memory stack, it will point on the first position. And a very specific characteristic of ARMv7 is that it grows downward. So you will start with less memory and go every time that you advance positions or addresses, you will be increasing your memory. And this stack pointer is used mostly when you want to store temporary values. So if you don't want to store your values permanently on your memory from your computer, you will use the stack pointer in order to hold them temporarily. And then you might use those variables to perform something else that will eventually be stored in the actual memory. The stack pointer, we won't be seeing more of this today, so it's okay if you just know that it exists, that that specific type of register exists, and that it's used to hold temporary values. But yeah, we won't be seeing more about the stack pointer today. And the last two are called linked register. So linked register basically stores the return address when calling a subroutine. So if you're familiar with traditional programming languages like Python, there's sometimes where you call a function, right? So if you are executing a block of if else, and then if your condition is true, then you might execute that function. So link register works the same, but it stores the return address when calling a subroutine or an external function, or when using a branch with link. We'll be learning more about what branches are in the upcoming content, but yes, just know that the link register stores the return address when calling a subroutine, which also happens in Python as well. And the last one, which I would say is the most relevant one, is the CPSR. So CPSR stands for Current Program Status Register. So this is a special register. It even has its own name. So it's called CPSR, and we'll also be seeing that on our simulator online. This one is a special register, and it holds condition flags. So it holds four different types of flags. So negative, zero, carry, and overflow. So negative if the number is negative, zero if the number is zero, carry if you have a carry, like in when you subtract and the number is more than 9, then you put the little 1 on top on the next number. So that's a carry. You are doing a carry on your addition, subtraction, or whatever operation that you're doing. And finally, we have the overflow. So overflow is when you go more than the 32 bits or the bits that you were supposed to have on your register. So these are the different types of flags that are out there, and you can actually look for this specific register if you would like. CPSR actually has a lot more in depth than what I'm just explaining right now, but it's okay if you just now understand the different flags that exist and how to use them. And these flags are used because they serve as comparison results from specific instructions. So in assembly, you cannot do if else because that doesn't exist. And the way that you do it is using flags. And these flags are the ones that are over here, and that we will be learning the different patterns and how to spot them in your assembly code. So, yes, this register is actually a pretty big deal because it's your way of making conditions and if statements on your assembly code. Because again, you cannot do if else, or you cannot have case 0, case 1, case 2, as you would do in a language like Python. In assembly, it works differently, and it works by using branches and flags in order to know the status of your program. We'll be seeing more of that with examples when we advance, but it's just for you to know that this is a special register in your assembly, well, in your ARM architecture. All right, and lastly for this set, talking about registers and memory, there's another important word, which is called word, which is it's very redundant. So in computer architecture, the term word means the natural size for the CPU, so where you will be storing your registers. And a word is equal to 32 bits. So when you are talking about computer architecture, it's very common that you will see half word, or double word. Because when they say word, they mean the largest amount of bits that you can store in a register. So instead of saying 32 bits, you can say RMB7 can store one word, and one word is equal to 32 bits. Keep in mind that word size changes between architectures. So RMB7 has 32 bits, but I'm pretty sure that other chip architectures have different sizes of words. And yeah, this is if you are into computer architecture, or you study something like robotics or electrical engineering, I'm pretty sure that on your exams you might be, your professor might be asking about how many words are on this specific CPU architecture, and then they might give you a set of bits for you to form the different words that can be formed with the space that you have free in memory. This one is just a term which is good to know. We don't really use it much. I mean, it's not relevant for the things that we'll be doing today, but it's just for you to know in case you hear this term on videos or online, for you to know that you're aware that it exists. Okay, so now going into the interesting part where we are going to be doing our code. So I cannot just go into my simulator online and start typing the code, because you might get a bit confused on what how everything works, because I think it might be a lot. So it's better for me to break down the different instructions that exist and explain them on how they work and what they mean, with um, not with natural language, but with coding languages, so regular coding languages. So I'll be using Python in order to compare the two codes. So I'll be placing one code in assembly and then the translation of that code in Python, so you can see how it relates. Before starting to see the different instructions that exist, we need to understand what an instruction is. So an instruction is a 32-bit binary code that tells the CPU to do something. So it can be either add something, subtract something, store something, load something, compare something as well, move some data, even. So instruction is just telling the CPU what to do. And this is just a line of different binary numbers combined that mean a specific thing. So in this example, we have our assembly code, which is add R2, R1, R2. So what does this mean? That you are adding R1 plus R2, and the result, you will be storing the result in R2. But this assembly language, your computer won't understand that language. You might understand that, but your computer won't understand that. So the way that you're going to do that is that the assembly code is translated to machine code, or binary as we know it, the zeros and ones. So this instruction in here translates to these set of bits in here. And you might be wondering that this has 1, 2, 3, 4, 5, 6, 7, 8. So 32 bits in there. I know the zeros are weird. I just mistyped them, but the instruction is of 32 bits. So this is a breakdown of the instruction, of a typical instruction. Actually, the position of the bits in here means specific things. So a typical instruction contains the following. So you have your condition field at the beginning, then you have 3 bits in here, then you have your opcode. So your opcode is the type of instruction that you're having. In this case, my instruction is add, but it can also be subtract, and it can also be a whole other sets of instructions that exist. But in our case, our opcode is add. And depending on the combination of bits that I have, is the specific opcode that I'm going to be sending into my binary language. Then we have the set condition codes, we have the first operand register, and our destination register, which is RD. So all of these numbers, they fill out these different categories, and this is how actually the computer understands your code. So now you know how your computer actually processes those zeros and ones. So I know that through your whole tech life, or no matter how long you've been in tech, you know that zeros and ones are the basic unit for all computers. But have you ever wondered how those zeros and ones are being processed? I mean, at least when I was younger, I had no idea. I just knew that they existed and that computers could only understand zeros and ones, but I didn't know how was the process towards that. So on these two sides, I'm actually explaining how computers process those zeros and ones, and it's just by translating your assembly language into machine code, which is this one, and inputting those different bits into these different sections, which each chunk has different amount of bits, and using your opcode, you identify which type of instruction is it going to be. So if it's an and, it will be 4 zeros, but if it's an or, then it will be a different combination of 4 bits as well. we have a question in here. I think Jocelyn said that she'd share it in the beginning's weird channel Discord yesterday, but I don't see the slides there, so I might be mistaken. Oh, yep. I mentioned that I was going to share them yesterday, but as I added new slides today for part 2, I'll be sharing them today. She's mentioned she's going to share all the slides today. Yep, correct. Thank you for mentioning. Okay, so for now, just keep in mind that your assembly code is not actually what the computer is understanding, but that assembly code is being translated to binary using this nomenclature in here that has different fields. We don't need to understand them all, and I'm not going to make you translate instructions into binary because that's just another whole set of low-level programming. I mean, that's just way below everything that we've seen today. So yeah, we'll just be using the regular assembly instructions in here, which hopefully are a bit more human readable than just typing random binary numbers. Well, they're not random, but yeah, in a way they're random for us. Okay, so if you were here yesterday, you remember something that I mentioned about execution cycle, but I didn't go quite a bit in depth because I wanted to explain more things first. So the execution cycle is just how your computer does this process. So how your computer translates assembly into binary. So it's not only selecting in here, but it's also a whole other sets of steps. So the first thing that you're going to do is fetch. So you start over here with fetching, and the CPU reads instruction at the address in PC. So if you remember what PC is, it's program counter. So you have your program counter in there, and you are going to read the instruction at that specific address because it's the next address that's following. After that, you will do the decoding process, which is over here. And the decoding is just basically CPU looks at the bits to figure out what the operation and operands are. Because of course, in every operation, you also have operands. So in the decoding process, your CPU wants to figure out which bits are which in order to classify them correctly and perform the operation seamlessly. And the last one is executing. So your CPU finally performs the operation, which can be either add, subtract, store something, or retrieve something. And that execution, guess what? It goes into the ALU, which is the arithmetical logical unit. So if you're familiar with computer architecture, and as yesterday we were mentioning that the ALU is the only place where the computer can perform mathematical operations. So once your instruction is being fetched, once your instruction is being decoded, it has to be executed on the ALU, which is inside your CPU. And the last step that you do is that you write the result stored in the destination register or memory. So your result from the ALU is being translated all the way down here into your memory unit, which the memory is where everything is stored, and you can store the result of your operation in there. So this is called execution cycle. You can look it up as that to see how computers actually process all of the bits. And this is just how it works once you have the information that you want to store and the information that you want to process as well. All right, so time to move on and learn some of these instructions. By now, I think I just showed you the addition one, but there's a whole other set of instructions that we're going to learn. So try to keep record of this because we're going to be using them when we start writing our code. So if you think that you won't remember, just take some notes or try to remember them so we can see them in the future for the exercises. So the first instruction that we have is called mov. So mov, as in English, is move. So this works to move immediate or register to register. So if I want to store something and move it to a specific register, I'm going to be using mov. So this how it works. I have the instruction first, and then I have a translation at the bottom. So for all of the slides, the section that is with another font, so the mov R0 hashtag 42, that's the actual instruction. And then what I wrote on the second line, that's just explanation. So that's not assembly code. That's just my explanation to you. So the first line, it says mov, which is move. And then what I'm going to be moving is a number 42 into register R0. That's why in here, now R0 equals 42, right? So I'm moving 42 into R0. So R0 equals 42. Easy, right? So just simple instruction. I'm saying which number I want to store, and I'm storing that number into R0. Great. And that first instruction is called mov. Then two more instructions, so addition and subtraction. So these ones are used to add or subtract two registers and store on another register. So our instruction goes like this: add, and then the register where I want to store my value, and then I have R0 and 5. So what does this means? That I'm going to be adding R0, so register 0 plus 5, which is the next value in here. And I'm going to be storing that on R1. So it's the same for subtraction. Just change the add in here to sub, and you will be doing subtraction. So you can also add to register. So you can have R2 plus R0 plus R2, and then you can store that in R5 or whatever register you want to store it with. Or you can add just regular numbers like 5 in there. Your assembly actually also understands hexadecimal, so you can also add hexadecimal numbers. But you set the hashtag to let it know that it's a decimal number. So from 0 to 9 on combinations of those. Yep. So for now we have mov instruction to store a value. Well, not store. Let's say move. And then we have addition and subtraction, which is add and sub. You store on the first one, and then your two operations are in here. So R0 plus 5. Okay. So all good. Remember that if you have questions or comments, you can always let me know on the chat so I can be aware about what's happening. Okay, and then next, three instructions: and, or, and not. So these operations are there to perform logical bitwise operations on registers. So what does this mean? If you want to do an and between two registers, you will just do and R3, R2 on R1. And what does this mean? You will be performing the AND operation between R2 on R1, and you will be storing the result in R3. So if you have seen on your classes or college courses about how are these called, logical gates or Boolean algebra, you might be familiar about how AND, or, SOR, NOT, XNOR, all of those operations work. So for example, AND is that you multiply the two numbers. So you will be multiplying R2 plus R1, which are the bits. So you're multiplying the bits, not the actual numbers. And then for OR, you're adding the bits. And then for NOT, you're changing the bits. So if you have 0, then that bit will be 1, because you're performing a NOT operation on that bit in there. I'm not going to go really in depth on how these operations work, because we are not going to be seeing them on the exercises, but just keep in mind that your logical gates that your professors are saying and might be boring for you at that time, and you might not understand what they work for. Those logical gates are also the basic unit for things and how everything works at a low level format. Over here, this MVN, that's not. So I don't know why designers or RB7 decided to call not MVN, but yeah, MVN stands for not. So you're performing a not operation on R5, and you're storing that on R6. So if R5 is equals, if in my register 5 I have the value 0 and I perform MVN, then I will be having 1 now, because I performed a not operation in my register 5 and I stored that on my register 6. Right, so far we've seen our mov operation, which is to move a value. We have seen addition and subtraction, and we have seen a couple logical operations like and, or, and not. So let's see what's next. Okay, next we have the shift left or shift right, some bits. So these ones specifically, they are there to shift something, as the name says, to the right or left. So LSL is shift left and LSR is shift right. So how this works, if you type LSL and then the register where you want to store your result, and then R0, and then the number of bits that you want to shift it. So in this case, I want to shift the register 0 by 1 bit to the left. So all the bits will be shifted 1 position to the left. And if you do LSR, then all your bits will be shifted one position to the right. So you might be wondering, okay, I understand the concept, but why shifting? I mean, why would I care if I move something to the right of left? I mean, that's just unnecessary. And the answer is no, it's not unnecessary. You can actually perform certain operations by doing shifting. So there's this whole topic about using left shifts in order to multiply something, and you can actually look it up to know how it works. But in assembly, you cannot do direct multiplications, so I'm not going to show you instructions that's called mul for multiplication. So no, that doesn't exist on RB7. So the way that you do it is through using shifts to the left. You can look it up as well in there. But yeah, so shifting is important for some specific operations. We won't be using shifting today, but just know that it exists and that it is important. Oh my god, I didn't refresh the page and Twitch stayed on the loading screen, so I missed 40 minutes. No, that's too bad. No worries. You can watch the recording as well. Right now, I'm explaining the different instructions that are in assembly. But yeah, shift use cases have always been confusing. I completely agree with you in this. So, shifting is important when you want to configure or perform specific operations on your bits to add masks, for example, in combination of logical operations like and, or, and not, and you combine those with shifting in order to, have the actual output that you want on your bits. Because on your computer, you cannot just say, okay, I have 4 bits, but I want to convert my third bit into a one, and I want to change the last zero to a one. Like, you cannot just choose with which bits to change or to read. So, the way of doing that or accessing those bits is through shifting and logical operations, which in our case are the and, or, not, and all of those operations. So that's why it can get a bit messy when trying to deal with those bits. But with practice and seeing some case scenarios, I'm sure it will come easily as well. I will not be getting into these really in depth, but just keep in mind that they're important. Okay, and moving on, these two instructions, they're really important. Why? Because LDR is for loading from memory and STR is for storing to memory. So they're different. Don't confuse them. They are different. So LDR is to store a value, well, load a value into, sorry, I said store, is to load a value from the memory. So you basically want to retrieve something from your memory and store it in the register that it's in here, which in our case is R0. So in our case, I'm retrieving the value that is in register 1 from memory, and I'm storing and I'm reading that in R0. And then for the storing, it's different. So we use str, and then we read from register 2, and we store that into R3, which is that memory address. So I'll be storing the value of R2 into the memory address R3. I know it might sound a bit confusing between these operations, but I promise you I have a table further along that explains the differences between these instructions. So load, you can see it as a way of reading your memory, and storing, you can see it as a way of actually saving the value on the memory from your computer as well. Right. Then we have CMP, which is compare. So this one, I would say it's very useful because it's a way of comparing two registers in order to set flags. So as I was mentioning before, you cannot do if else with specific conditions. So in Python, we do if 7 is greater than 2, then I'm going to execute this. So you can do that easily in Python language or any other high level language that you know. But in assembly, it doesn't work like that. You need to use flags and you need to compare different registers in order to know where to jump in your program, in your assembly program. So CMP, how it works, you have CMP and the two registers that you want to compare. So in our case, I'm comparing if are 0 or 1. But at this moment, I don't know what I'm going to compare because I need to select a flag, and I'm going to show you which types of flags are out there and how to use them on a complete program later on as well. For now, just keep in mind that CMP is to compare two registers, and the syntax is just CMP and the two registers that you want to compare to. I never heard of this when I took computer organization on ARC. Well, it's nice that you are learning this now then. Right. Okay. So the next instruction is B and BL. So B stands for branching, and the first one, B alone, starts for branch to jump somewhere, and the BL is to branch to call a function. So the first one is just typing B loop. And in this case, I'll be jumping to the label that's called loop. So I can have my whole assembly program and I can have different labels. So I can have my label for start, my label for end, my label for loop, and so on. So I can have different labels. And if I do B loop, then that means that when I reach that line in assembly, I will jump to the section that has a label called loop. It can be any label name, so you can name it like label 1 or addition, function, whatever, and your assembly program will jump there once you reach your B loop or that specific line. And then the second one is BL, which is BL and then the name of your function. In this case, it's to call a function. So if you want to call a function immediately, then you will be using BL and then your main function in here. BL, they're different. So we have B, which is just B alone, and then the name of the label where you want to jump, which in this case is loop, or it can be any other name labeling. And then we have BL, which is to jump into a function, which is BL and then the name of your function. So right now, we learn about comparing and we learned about branches. So they actually relate each other. Because if we compare something and the result of that comparison is true, then I want to jump somewhere else on my program. And that's just the way in which, for example, Python works, where you are doing you are comparing, I don't know, two numbers. And if the operation is true, then you perform a specific thing, and if it is false, then you perform another thing. So in this case, we are comparing two registers, and then you can use branch to jump to that other section of your program. So let's say that you're comparing two numbers and the comparison is true, then I can jump to B is true, and then I can execute that section of assembly code. I know right now it might be a bit confusing just by explaining myself with words, but I will be, well, there's an example further along on the presentation where we are going to be mixing all of these concepts together. Okay, before moving on to the examples, it's important that you understand the differences between move, store, and load. So move, what it does is that it copies a value between registers. So the registers that I choose there, it's the value that I'm going to be copying in there. And keep in mind that we're talking about registers and we don't have memory access. It's just basically moving data inside the CPU. So I just want to move it, but I'm not storing it into the actual memory. I'm just moving it temporarily, but I'm not going to be storing it permanently on my CPU memory. And then the second one, which is a store, I'm storing a register value into memory. So how this goes is register to memory. So from register, it can be register 1, register 2, and so on. And I'm moving that register into the actual memory for my computer. In other words, we're saving the register content into RAM memory at the specified address. So let's say that I want to store 5 in address 0x01. So I'm going to be storing that value into my RAM memory into that specific address. So that's why it's called store. And then the last one is called load. So load, it basically reads a value from the memory into a register. So it brings the value, it retrieves the value from the memory, and it translates it into the register. So it works all the way back. So memory now to register. And this process is when we are reading the data from RAM into a CPU register. So I'm retrieving what's in the RAM and I'm putting that into my CPU register for me to use into whatever part of the program that I wanted it to be used. Okay, so I'm just going to leave this table in here in case you want to process it for a while. I know they are kind of similar, but in a way they're different, and it's important to understand the key differences between these ones as well. If there are any questions or comments, you can drop them in the chat now so I can be answering them as well. Yeah, and I also want to rest my throat for a bit. I think I was explaining so many things, so many concepts. So yeah, I just kept talking nonstop. Okay, let's see what's next. Okay, so this one's the last one before moving on to our coding practice, which will be interesting. So this is a place where we're going to be learning about branches, the CMP for the comparing, and also the conditions for the flags. So in here, we're going to be mixing three of the concepts that we learned previously into one concept on how to do conditionals in assembly language. We have a question over here. Basically, mov is for like copying values between registers, like if you're setting variables. That's correct. Store is mostly for when you're done with the calculation and want to write back to memory. Exactly like you said it, completely right. And load is for from getting the data from RAM into register. Exactly. Yep, you said it perfectly. Yeah, that's basically how it works. I know it might be confusing and there's so many things to understand, but just keep your concepts clear, go into the basics, and try to understand the differences between each other. And well, this hacker wrote a very nice explanation, so you can also go ahead and read that one as well. All right, so seeing this slide, there's many things to understand in here. I think I could have done better with the slide, but yeah, let's try to see what this means. So as I was saying, in assembly, you cannot just do direct comparison. So you cannot just do if else and jump into a loop. So that's very hard to do in assembly, and it works differently. So in assembly, we use a combination of CMP, flags, and what was the other one? And the branches. Yeah, the branches in order to perform these types of operations. We have a question over here. If store load is moving to and from RAM and registers, where those cache stand? So your cache memory, or I think I mentioned it as flash memory, is where your program data is stored. So I think this one is not related to what we are seeing right now. There's a bit lower level, but your OS should handle that automatically. Yes, we're not going into cache memory right now, but that's actually an interesting question. So yesterday we saw the differences between RAM and ROM. In this case, everything that we're dealing when I mention memory, I'm referring to RAM memory, and ROM is where the program data is stored. So basically, our assembly code, it will all be stored into ROM memory of my computer. So that's the two ones that we are interacting with right now. All right, so going back to this, I'll be explaining this. So CMP, we already saw this. This is to compare two registers and to set flags. But CMP is also useful with branches because it checks flags and decides whether to jump or not. So there are specific flags in assembly. So these are not the only ones that exist. I just placed in here two flags, which is BEQ and BNE. So BEQ stands for branch if equal, and BNE stands for branch if not equal. So if I want to compare two numbers that are equal or not, I will be using BEQ or BNE as I have in here. So in here, I have a specific assembly code. So I have compare. So I'm comparing R2 on R1, and then I'm doing BEQ equal label. So I'm going to branch if it is equal, and I'm going to move to this label, which is called equal label, which is just a section, um, which is just a section on my code. And if it is not equal, so BNE, then I'm going to be moving to my label that's called not equal. And remember when I was talking to you about the special register that's called CPSR? So CPSR is the one that takes care of all the flags. And in this case, we are using flags. So the flag in here, if it's equal, it's the flag is set to 1. And if it's not equal, it will be set to 0. What does CMP stand for? Compare. So CMP, compare, it actually makes a bit sense. So yeah. So this is specific code that's in here. It's to compare two numbers, and I'm jumping between different branches in order to, depending on in which case my number is going or which values I have in my registers. We'll actually be doing an exercise of comparing two numbers if they're equal. So no worries if you didn't get this at a whole level. We'll actually be getting a bit more in depth in an exercise that I prepared for you further along. All right. Okay. So before moving to the coding practice, I'm going to make a short 5 minute break so I can grab some water and also for you to rest before we go into the coding exercises. So I prepared a total of three coding exercises that we'll be doing. And I'll be sending out the simulator right now on StreamYard. There we go. So feel free to explore it. We'll be writing all of our code in there. So yep, I'll be hanging around and I'll be back in about 5 minutes. Feel free to drop your questions on the chat or your comments as well. When I come back, I will be seeing them. All right, there. Back. Great. So hopefully you also got a short break before we start doing the coding exercises. We're going to be doing a total of 3 exercises. They increase in difficulty, so we'll be starting with a simple one, and then we'll be doing a medium one, and then a hard one. So yeah, first thing that I'm going to do is introduce you to the simulator online, and then we'll see how it all works and what are the different buttons that are in there, and then we'll be starting writing the first coding exercise in there. Okay, so moving on in here, I'm going to change it, and I'm also going to read your comments. So, asked AI, the cache management seems to be handled by the hardware directly. Yeah, then it doesn't relate itself. Can you go back to BBL? So the branches? Yep, of course. Let me go back. This ones you mean? But either way, yeah, I don't think this is something assembly deals with directly. You're right, and also thanks for clarifying. Never mind. All right. Hello, hello. I Google cache. It says between registers and RAM in memory pyramid. That's why I am confused. Hmm. We have another explanation in here. So to explain cache a bit better, your hardware handles it automatically based on how you arrange and access your data. For example, let's say you have an int array with 10 entries. If you were accessing the fifth entry in the array, it will grab, for example, the fourth and sixth in anticipation. I see. That way, the JSON data is loaded into memory since your CPU is smart enough to know that you'll probably access nearby data later. All right, thanks for the clear explanation, and I hope that was clear for the people that were asking. Thank you so much. Great, so let's continue with our coding exercises. And the first one that we're going to be having is comparing two numbers. So I mentioned you before that for comparing two numbers, we need a set of 3 things. So we need the comparison, which is the instruction CMP, and then we also need our branches, and we also need the flags. So 3 different concepts in there. And on our instruction, we want to set R3 to 1. So register 3 value to 1 if it is not equal. So if the two numbers are not equal, and then we want to set R3 to 0 if they are equal. You can set any flags that you wish, and it can be any register. I'm just choosing register 3 and register on whatever register I'm going to be choosing, but it can be any register that you want to choose from the ones that we saw that are general purpose ones. Okay, so let me share my screen with the simulator thing so you can actually go ahead and see it as well. Right, so it should be showing in there, and I'm going to make this a bit bigger. Is the screen okay in there? And I want to ask the chat, can you all be able to see what I'm typing in here? Like in a decent way? Because sometimes when I do VS Code, they tell me that it's sort of small. So just want to be clear on that. Yes. Okay, then I'll be moving forward. So for this exercise, they're basically asking me to compare two numbers, and I want to store in R3, so R3 over here, which is this register, a specific value depending if it's equal or not equal. So to start, what is the basic instruction that we saw? So it was move, right? So we're going to start by moving my two numbers into my registers. So let's say we want to compare number 5 and number 6. So we'll be starting off by typing mov. And then what was the first thing that we need to do? We need to type the register where we want to store my number. So let's say I want to store it in my first register, which is R0 over here. And in R0, I want to store in there the number 5. Perfect. So I have my first assembly instruction. So I do enter, and then I do the same. So now I want to store a different number, but this time I will store it on R1. So in register 1, I will be storing number 6. There we go. So now if I actually go ahead and compile this, and then I do a step into, you are seeing now that it loaded in R0, it loaded the number 5 in here. And then if I step into again, now in R1, it loaded 6 in here. So this is just how my values are being placed in here on my different registers that I have. So this is actually how your computer is storing your registers when it is compiling your assembly code. So let me reload this so we can start clean. I'll just paste what I had. Perfect. So we have now I have my two numbers that I want to compare. So I'm comparing number 5 and I'm comparing number 6. Okay, so now that I have basically, if I was talking about Python language, I now have my two variables. So I have A, which is equal to 5, and I have B, which is equal to 6, which was basically what was shown. Let me show it again, which was basically what was shown over here in our example. So we have A and B, which are being used using the move instruction. And then the next thing that we want to do is compare these two numbers, right? So what was the instruction that we used to compare? So it was CMP, right? So we're going to use CMP. And the input parameters for this one is two registers. So which registers am I going to be selecting here? So I'm going to be selecting register 0, of course, which has the 5, and register 1. So I'm here, I'm just basically saying to my code, and I'm going to leave a comment in here, saying that I want to compare these two registers. But I mean, I'm just comparing them right now, but I'm not saying anything. So I'm just making this comparison, but what do I want to obtain for that? So in here is when I'm going to use one of the branch instructions that we used before. We have a question here. What is CMP? CMP is for comparing. Yes, CMP is for compare. So after doing the compare in here, we need to select a specific branch or a condition that we want to follow. And if I go back over here on the slides, remember that we talked about these flags. So BEQ, that it stands if it is equal, and BNE if it stands for not equal. So in this case, we can use any of these two. So I can check if not equal and equal. I'm going to go with the first one, which is BEQ. So I'm going to choose BEQ to check if my registers are equal. So over here, going into my code, I'm going to type BEQ. And what's the next thing that I'm going to do? I need to jump into a label. So labels in assembly are, for example, this one. This one is a label that's called start. I'm going to go ahead and create a new label. And that label, I'm going to call it equal. So if my comparing in here these two registers, and if they are equal, what do I want to do? I want to jump over here into equal. So I'm going to type in here the name of my label, and my label in this case is called equal because I want to type in here, down here, the instructions that will be released once I jump over here. So I'm going to type in here, jump into label equal if the two registers are the same. So basically, R0 equals to R1. Right, perfect. Okay, so in case that these two registers are equal, what do I want to do? I want to set a specific value on my register. So I'm going to do mov, and then in R2, I'm going to set specific value. So I can set, what do you like? So I can set 5. No, I can set 2 if they're equal. So set register R2 to 2 if my two numbers are equal. We have a question here. Does the indentation matter? It's not supported to be indented under the label. Suppose, yes, I think it matters, and when I run it, it's going to mark an error, but I think it won't. I honestly don't remember, so I'll just see what happens and try to correct my code while I'm doing this. It's a while since I do stuff like this, so if I make a mistake, just my apologies. I'll try to correct it once we see what error it is. So in here, we know that we're setting the R2, so set register R2 to 2 if my two numbers are equal. So right now we just covered one case, which is if the values are equal. But what happens if my values are not equal? Then I'm not going to jump, and then I'm just going to go into the next instruction. And the next instruction, if they are not equal, I'm going to store in R2 a different number. So I'm going to store, let's say, 3. So set register R2 to 3 if my two numbers are not equal. There we go. And yeah, and then after finishing this, well, I can just end my program, right? So I can use my B instruction, which is branch, to go over to the end. And I'll just create a new section in here that will be called end. And this will just be the end of my program. So not much to include in here. Okay, so let's do the indentation in there. There we go. So hopefully this is pretty straightforward. I'm going to be running the code and also see how the different registers are interacting with each other. So again, I'm storing, saving my two values in here that I want to compare. So I'm saving 5 and 6. Then I'm comparing these two registers. And then if those two registers are equal, then I'll be jumping into the equal section and storing a 2 in register 2. And if they're not equal, then I'll be storing 3 in R2. And once whatever happens, I'll be branching, so jumping to the end. And the end is just crash the program. So nothing in there. We have a comment in here. One thing to note probably is that if you didn't use bn, it will have to go to the mob R2 #2 command again. Yeah, because it'll be repeating itself. That's also a way of making loops. Actually, by using these labels, you can also do loops where you are looping and basically jumping into the label that you want over and over again as well. Okay, so let's try to run this. So compile and load. And let's see. So the first instruction in here is loading my 5 into R0. So let's see. 5 is loaded into R0. Then next instruction, I want to, I'm loading 6 into R1 over here. And then the next instruction is the compare. So I'm going to compare R0 and R1, which are these two registers. And if they are equal, let me see what I said. So if they're equal, I should see in R2 a number 2 in here. And if they are not equal, I should be seeing a number 3 in here. So let's see, I'm doing the comparison in here, comparing, and there we go. So now in R2, I'm seeing a number 3, and that just basically means that my numbers are not equal. So let's try to change the numbers that I had in there. So let me just retrieve everything. So let me change the numbers now, 5 and 5, to see if I get the 2 now. So let's do this. So I have 5, another 5, and they're equal. So now I'm seeing number 2 in here. So in this way, I'm basically now comparing two numbers in assembly. So hopefully by doing this, let me refresh this again. So by doing this instructions in here, you are basically comparing two numbers. And the two numbers that you're comparing are the ones that you type in here. And these 3 and 2 just work as print statements if you would like to relate it to Python language as well. All right, so any questions, comments before we move on to the next exercise? I'll just wait a few moments to see if there's any questions. All right, I guess we are good to go. Let me stop sharing this one. Okay, so now moving on to the next exercise. So for the second coding exercise, we'll be using a combination of two instructions. So we'll be using sub and add to perform the following expressions. So my expression is 5 plus 3 minus 4 plus 2. So this is how you would do it in Python. So you have your result and then you want to print that result and, well, perform the output in there, right? So we're going to be coding this up in assembly language, going step by step by using these instructions that I have over here. So let's see. I'll be adding this one now. There we go. So let me erase this one. Well, I'm actually going to add this one into a slide over here. So once I share it, you will be able to see it in there. So I'll just add it in there. Oh, this is too big. Okay. I'm just going to make this in small font and then you can just zoom it in. There it is. So here's the coding exercise number 1. There we go. Great. All right, so now I can't delete this one. Okay, so I'm adding the exercises on the slide in there so you can see it as well. What is the button to run the program? So you will first do compile and load and then step into. And step into will be executing line by line. So you'll be seeing the outputs in your registers over here. So as I was mentioning earlier, you have your different registers over here. And in here, we're seeing the special registers that I told you about. So we have our stack pointer, our LR, PC, CPSR, and so on. And then these ones are our stack ones. So this is a stack, which is actually used for other stuff. But yep, this one's for the flag in here. Oh, yeah, that's why registers are very important because they're basically in there on your computer memory. And they are the ones that we are interacting with right now. All right, so going back to the problem that we had to do, we need to do the operation. Let me see it again. So the operation is, let me type it in here. So it's 5 plus 3. And then we have minus 4 plus 2. All right, so that's the operation that we want to do. I already typed it in here on our assembly notepad. And the first thing that we're going to do is we're going to be starting and storing the 5 and the 3 that we want to have in here. Why? Because I can add these two together and then just do the subtraction on whatever happens on this side. So starting off with mob, and I'll be using register 0 and I'll be storing number 5 in there. Where's my number 5? And then I'll also be storing, but in register 1, I'll be storing the number 3. So now in here we have R0 equals to 5. And then over here we have R1 equals to 3. So we have our first set. And what do I want to do with these two? Well, I want to add them because I want to add 5 plus 3. So to add, I'll do add. And I store the result on register number 2. And I'll do R0 plus R1. So this one, it will translate to this. So R0, let me do it like this. R2, I'm sorry, equals to R0 plus R1. And the result will be stored in R2. So this will be hopefully an 8. Okay, so let's try. I'll compile this thing to see the output in here. So compile and load. So on R0 we have our 5, R1 we have our 3, and then in R2 we have our 8. Awesome. So everything's working correctly so far, and we have our first set of our math calculation. So let me refresh this again. Paste what we had. Okay, so now the next step is doing this thing, right? So we want to do the 4 plus 2, which is inside the parentheses. And we'll do it just the same way. So we'll be using a new register, so we can use register 3. And I'll be storing in there the number 4, which this basically translates to having R3 equals to 4. Then I'll be doing the same, but in register 4, and I'll be storing the number 2 that I have in here. So this will be 2. And this is the same as having R4 equals to 2. And what am I going to do after that? I have to add them, right? Because this is an addition, so 4 plus 2. So I'll be doing add and then the same. But this time I'll be adding 3 plus 4. So R3, I'll be storing in R5. And I'll be adding R3 plus R4. And this is basically as having R5 equals to R3 plus R4. There we go. And this will basically translate to having 4 plus 2, which is 6. So let's see if this works correctly. So let's compile this and run it. So we have our 5 first, then our 3, and then we will have the 8. And then in our 3, we'll be having, what was it? We'll be having a 4. So we have 4 in there. And then in R4, we need to have 2, right? Because it's the 4 plus 2. So we have 2 in here. And then the result, we'll be storing it in R5. So in R5, we need to be seeing 6. There we go. So now we have our 6 in there. So this means that we have our 2 additions correctly, and they are being shown in our registers correctly. So let's go back to our code. And we have a question in here. Can you do mov R0 4 since we already used 5 in add? Can we reassign registers to values? Let me see if I understand this. So I have mov R0 5, since we already used 5 in add. So I think I know what you're asking for is that if you can recycle the values that are in a specific register, and the answer is yes, you can use them as sort of variables if you would like it to see it that way. In my case, as I have different numbers, that's why I'm storing them into different registers. But if I were to store, for example, let's say that in R2 my result is 8, right? And then I want to use that 8 into a different operation. Yes, you can do that. But keeping in mind that this is a program where the user can input any values, then that register will change and then it will affect the program. But if I think what you're asking is that if you can recycle the values that are in the registers, yes, you can go ahead and do that if your program allows it. Okay, so far we have the 2 instructions. So we have the 2 additions in here. So now the only thing that we're missing is the subtraction, right? So our result for the first addition is stored in R2. And the result for the second addition is stored in R5. And if I want to do the subtraction, I need to do R2 minus R5, right? So I'll be doing that. So the next thing that we need to do is just do the sub, because sub is for subtraction. And we want to subtract, we want to store the result in R6, and I'll be doing R2 minus R5, which will translate to having R6 equal to R2 minus R5. There we go. And that will be our result. And now my result from this whole operation, which will be 8, will be stored in my final register, which is R6. And this will just be the end of our program over here. So let's compile and load this. Step into, so we have our 5 in there, then we have our 3, then we have our 8, 4 plus 2 equals 6, and I will do 8 minus 6, which will be 2. So now in R6 we have the result of our mathematical operation that we were doing. So just like that, it's easy to handle the different registers and how they work. In here you're seeing the actual addresses where the thing, oh my god, I have like 6% battery going on. Whoa, that's not good. Okay, but we have one more exercise moving forward, so let's see if that's going to work. All right, so in there, it's just basically the output for my math operation, and I'll add you the exercise in here. So coding exercise number 2, and let me add it so you can have it as well. Oh, I think I just deleted it. Well, I'll do it again and paste it on the slides once I share it. Okay, so moving on in here to our third exercise. So for the third exercise, we want to use AND to determine if a number is even or odd. So how are we going to do this? We're going to use this logical operator called AND to determine if the number that I'm having in there is even or if it's odd. So how this works is that to determine if a number is odd or even, we can use AND as a helper. So AND, how it works is that it will take the least significant bit of any integer and tell us if the number is odd or even. So in this case, we have 4, and 4 is this number, so the binary number that's in there in binary. And the least significant bit is a bit that's all the way at the end, so 0 in this case. And if we have 0, that means it is an even number. And if we have 1 on the least significant bit, it means that it's an odd number. So that's why 5, it's an odd number. So this works for all numbers that you convert to binary. So if you have like a 10 in binary, and 10 will end in 0 because that's an even number. So knowing that logic, knowing that my least significant bit will tell us if an integer is odd or even, we can use that as an advantage in order to do our coding here. So when we do, for example, AND, register 1, register 0, and 1, we are masking out all the bits except for the least significant bit. And the least significant bit is the one that's all the way at the end. So so if you have register 1 equals to 0, that means it's an even number. And if we have R1 equals to 1, then that means it's an odd number. So the result that we have in our register, it will determine if our number is odd or even. So I actually place in there an operation for you to see. So let's imagine that in my register 0, I have the number 4. And then I I perform an AND operation between number 4 and 1. So basically R0 and 1. And that will output to having 8 zeros. And my last number is my least significant bit. So if my least significant bit is equal to 0, then that means that my number is even. So this can compare to any number. So we're going to be doing AND operations between, 5 and 1, 7 and 1, 10 and 1. And having performed that operation, it will determine what my last bit will be in there. So in that case, my last bit is 0, and 0 means that number is an even number. So let's try to apply that logic into our assembly code, and we will actually be doing this. So I have 3% battery. I need to go for my charger, and I need to restart the session because I will have to use a different computer. I know it's very confusing, but I'll be back in less than 5 minutes, so 3 minutes, and I'll start the stream again so you can rejoin. I'll see if it doesn't end, But let's see what happens if I close my computer and open up the stream from a different page. Hey there, back. So that was faster than I thought, honestly. So let me just open up my slides on this computer so I can continue where I was at. So CPU later, let's see. Great. So far we've done like 2 exercises by now, and I have to admit that the last exercise is the one that's more, well, it's not very confusing, but it's definitely different to what we are used to, because we are basically using these and operations in order to determine if a number is odd or even. I know that it might be weird that from having an AND operation, you can determine if a number is odd or even, but it's actually possible if you go down into the bit level of, as I already showed you on the slides that we had. So let me go back to our zip later online so we can start coding that, that assembly code to determine if it will be odd or even. There we go. And let me make this a bit bigger. So hopefully you should be able to see it quite fairly good in there. All right. So where was I? Okay. So the first thing that we're going to do is that we want to move the value that we're going to be comparing into any register. So simple, right? We want to do mov, and then in register 0, let's compare 7, for example. So we want to determine if the number 7 is going to be odd or even. So as I mentioned, the first thing that we need to do is to perform an AND operation with the number and the number 1. Why? Because we want to extract the least significant bit. So we're going to do an AND operation, and then the result, we're going to store it in R1, and we want to compare 7, which is stored in R0, and we want to mask it with 1. So what this translates to is that R1 is equal to R0 and, where's my and symbol, and 1, which works to extract the least significant bit. So we already have our AND instruction in here to extract the least significant bit. And what happens once I extract the least significant bit? So if you remember, least significant bit equals to 1. That means this is, I think this was odd or even. I don't remember. I will need to go back and check it. And then least significant bit equals to 0. That means this is even. There we go. So let me just go ahead and check the slides and share with you as well so I can remember if the 1 and 0 it's actually correct. Slides Google. Yeah, because I also confuse myself knowing which one is which, and I just want to be completely sure before I continue with the coding there. Okay, there we go. So I have my slides over here. Let me share it back as well. Share. All right, so we were all the way over here. Exercise number 3. There we go. So if the register is equal to 1, it's even, and if the least significant bit it's equal to 1, then it's odd. I think I said it the wrong way. So if it's 0, it's even, and if it's 1, then it's going to be odd. So let's update that one into our code as well. And we have some comments going around in the chat. Yes. You format with, wait, those 0 count as an even number. No, you were right. Yeah, I think I was mistaken. So now we have that 0 is the even number and 1 is the odd number. So yeah, I was right all the way. I just wanted to double check on that because I'm a bit rusty on this as well. Okay, so we already moved the value of 7, the one that we want to determine if it's odd or even, and then we are performing the AND operation by extracting the least significant bit. So once that we extract our least significant bit and store it in R1, what's the next thing that we're going to do? We want to do a compare. So we're going to compare my register 1, which is the least significant bit, and we want to compare if that result is equal to 0. So 0. And if it's equal to 0, what does it mean? Is that the value is equal. So I want to branch out if equal. And I'm going to move on to my label that's called is even. So let me create a label that's called is even in here. So if my least significant bit is equal to 0, then that means that the number is even. And if the number is even, then what I'm going to do, I'm going to store in my register 2 a number, an even number. It can be like 6. So if I have an even number, move 6 to R2. So if we have an even number, I will have 6 on my register 2. And what happens if I don't have an even number? So if it's an odd case, then I will just be moving in R2 a different number. And I can say I can move 5. So if I have odd number, move 5 to R2. Awesome. And then once we do that, then we'll be reaching the end. So I'll create another label for a branch that will jump all the way to the end. So I'll create that label end, and this will be final. There we go. So this was not very hard once we understand the concept of the least significant bit using AND. So we are performing AND to extract the least significant bit, and then if the least significant bit is equal to 1, then it's odd. So we will go all the way over here. And if it's 0, then it means it's even, and we'll be jumping up to this one. So if we have an odd number, we'll be storing 5 in R2, and if we have an even number, we'll be storing 6 in R2. So let's go ahead and run that. So compile and load, and we'll be stepping into. So we are storing our first number in 7. Our register 0 is equal to 7, and then our comparison sets that R1, so the least significant bit, it's equal to 1. So what does 1 meant? And then we're moving on. Hopefully we should be seeing the result in R2. So R2 has a register value of 5. So this means that my value in there is an odd number. So let's go ahead and try it again. Now with an even number. So let's try, instead of having 7, let's try doing 10 or 2, which is easier. So let's try doing that one. Compile and load. Step into. So we have our 2 loaded up in here. Then this actually has a 0 as a least significant bit. So we have a 0 in here, which of course it will output 6 in my register 2, which means that we have an even number. Great. So hopefully this is the code to determine if a value is odd or even, which honestly it's very different to doing it in Python language, where you use the divisible thing to see if it's divisible by 2, and then you determine if it's either um, even or odd. So yep, that was pretty much. Let me go back all the way to this one now. And so we can start wrapping up as well. Share screen. There we go. Right. So hopefully from here, we were able to do our last coding exercise. I'm also going to be adding that one in here. So let me just paste it in here before I forget. So I'll be pasting the last exercise for you in here, which is to determine if it's an even or odd number. So now you have all of the 3 exercises. If you want to go ahead, I'll be sending out the slides so you can review all of these instructions, which are the key to everything, honestly. So if you want to review them more carefully and try to do the coding exercise for yourself, I would definitely encourage that, so you can also practice for this as well. Right, so I will be wrapping up today. Sadly, this will be the last stream that I do for Beginners Week. But no worries, I'll be back on the next Global Hack Week, and I promise you that I will be having more robotics streams related. So I'll be making a post on AI and different APIs, well, cool APIs that you can use, and I'll be more into doing streams related to Linux systems, streams related to ROS, which is Robotics Operating System, and hopefully we'll be seeing something about electronics as well. So I'm going to go ahead and share this link with you on the chat. Feel free to give us some feedback about Global Hack Week. So things that you liked about the streams, things that you would like to improve, or even some recommendations about workshops that you would like to see. So please make sure to fill out that feedback form in there so we can see how you're feeling as well. And yeah, we have a question here. Please help how to obtain student ID or proof of participation from MLH used to sign up for the GitHub Student Developer Pack and Figma Education account. So for the Figma Education account, all you need is your school account. So if you use your school email, you should be good to go for the Figma one. And for the GitHub Student Developer Pack, that's a bit more challenging. So for that one, you also need to use your educational email, and then you need to upload a school schedule, some proof of your classes or your transcript or your university ID in order for you to get the license for the GitHub Student Developer Pack in there. Right, so hopefully that was helpful. I'll be wrapping up today. I'm very happy to see you all as always, and please make sure to tune in for the rest of the week, because there are several coaches that have really cool streams prepared for you all, and also different mini events that you can play around on the Discord channel. Bye everyone, and I'll be seeing you up until the next Global Hack Week.